Welcome to all. I am Parthivan. In this presentation, going to discuss about vapor pressure and compression refrigeration system difference. Followed by we will solve two problems regarding that refrigeration system. Let's see. Let's see one by one. This is the difference between the observation system and the compression system. The observation system uses low-grade energy like heat, therefore may be worked on exhaust system from IC engines, etc. The compression system using high-grade energy like mechanical work. The observation system moving parts are only in the bump which is in a small elements of the system, hence operation is smooth. The compression system moving parts are the compressor, therefore more wear, tear and noise. The system of absorption can work on low evaporator pressure also without affecting the coefficient of performance. The compression system, the coefficient of performance decreases considerably with decrease in evaporator pressure and no effect of reducing the load on performance in the evaporation system. The performance of compression system is adversely affected at partial load. Liquid traces of refrigerant present in piping at the exit of evaporator constitute no danger in the absorption system. The compression system, liquid traces in suction line may damage the compressor. Automatic operation of absorption system for controlling the capacity is easy, but in the compression system is difficult. This is the problem where we are going to calculate the coefficient of performance of the refrigeration system. This is ammonium based refrigeration system. The temperature limits of an ammonia refrigeration system are 25 degrees Celsius and minus 19 degrees Celsius. If the gas is dry at the end of compression, calculate the coefficient of performance assuming no undercooling of the system. The properties of ammonia are given below. At 25 degrees Celsius, the liquid heat to 98.9 kilojoule per kilogram, latent heat 11,166.94 kilojoule per kilogram. Entropy, the liquid entropy 1.242 kilojoule per kilogram Kelvin, as well as the 10 degree Celsius temperature of liquid heat 135.37, latent heat 1297.68, liquid entropy is 0.5443. From we can take the given data. T1 is equal to 25 degree, T3 is equal to minus 10 degree. We have to find out coefficient of performance. Solution: from the refrigerant table, temperature at temperature 1 is equal to minus 10 degrees Celsius, where we can taken the HF1 value, HFG value and the entropy of fluid SF1 value from the refrigerant table, where the entropy is same at initial and next stage S1. Therefore, the S1 is equal to S2. From the refrigerant table, according the T2 temperature 25 degrees Celsius will provide the HF2, HFG2, SF2 value. and then we can calculate the H2 value by using HF2 plus HFG2 value. For isentropic compression, S1 is equal to S2, so that from equation S2 is equal to S1 is equal to SF1 plus X1 HFG1 by T1 is equal to SF2 plus HFG2 by divided by T2. With the formula we can calculate the S2 value and the S1 value, and then H1, the enthalpy at the initial stage, is calculated by HF1 plus X1 HFG1 formula, where the theoretical coefficient of performance H1 minus H4 divided by H2 minus H1. The coefficient of performance is almost 14.38 according the input value. And then this is ammonia refrigerator operates between evaporating and the condensing temperature of 16 degrees Celsius and 50 degrees Celsius representative. The vapor is dry saturant at the compressor inlet. The compression process is isentropic and there is no undercooling of the condensate. Calculate the refrigeration effect per kg, the mass flow and power input per kilowatt of refrigeration and the coefficient of performance. Here you can see the properties of saturated liquid and saturated vapor R717 ammonia NH3. The temperature T is respective with enthalpy, entropy and specific heat according to the according to this temperature minus 16 degree Celsius, the enthalpy value of liquid 126.74 and vapor He 1442.91, and then the entropy of liquid 0.7248 and the entropy of vapor Sg 5.8433 and the specific heat of liquid 4.523 and 2.429 of vapor specific heat values. Here the H1 is equal to Hg at minus 16 degree Celsius. The S1 is equal to Sg at minus 16 degree Celsius. The first one is dry saturated vapor at a compressor inlet. The second one is that compression process is isentropic given, and then H2 value is calculated by using Hg plus heat capacity of temperature supersaturated minus temperature saturated. The refrigerating effect per kg H1 minus H4. Initial enthalpy and final enthalpy will, the difference will provide the refrigerating effect per kg, mass flow rate and power input per kilowatts of refrigeration will provide 1 by H1 minus H4, and the power input will be m power dot H2 minus H1. Coefficient of performance, refrigerating effect, working input The refrigeration effect already we have discussed. The H1 minus H4 work input means the H2 minus H1 value. Note, some data book gives the CP value for vapor ammonia refrigerant in the following format. The specific heat of superheated vapor CPV kilojoule per kilogram Kelvin. The according to the temperature, the super degree of superheat is decreasing at 10 degrees Celsius 3.518, at 50 degree of saturation temperature, and again 15 degree Celsius. The saturation temperature in the 50 degree Celsius provide the 50 3.145, and at 60 degrees Celsius 3.087, 80 degrees Celsius 2.993, 100 2.924, 120 2.872. Since degree of superheat is not given, any heat capacity CPV value taken may be considered even for the lower value of CPV from the table. No change in refrigerating effect, no change in mass flow rate. Finally, the power input will be 0.332 kilowatt. The coefficient of performance is 2.92 to 3.008. Thanks for watching. Within this, I will conclude this presentation. This continuation will be come by next part. Thanks for watching.